This is part 2 of the trig functions videos. We are going to introduce the unit circle, look at the difference between radians and degrees for measuring angles, examine some special cases of right triangles that will help us fill out the x and y coordinates of our unit circle, and then look at some examples of evaluating trig expressions using the unit circle. So this is our unit circle. It's called a unit circle because its radius is 1 unit. So no matter where we draw from the center of the circle to the outside of the circle is always going to be 1 unit. The other thing that is important to know about the unit circle is that it's centered at 0, 0. So when we are looking at coordinate points on the unit circle, we know that this coordinate point here is 1, 0. Up here we've got 0, 1, negative 1, 0, and 0, negative 1. So those points are easy to fill out because we know the radius of the circle is 1. But the other points are a little bit harder. So if I'm trying to figure out the coordinate point right here, what I'm going to do is first draw that radius in, because I know that line I just drew has a length of 1, since it's the radius of the unit circle. And I'm trying to figure out the coordinate points x, y that correspond to this point. And so what I'm going to do is drop a vertical line down here. I've created a right triangle where the base of the triangle is the length x and the height is y. We can call this angle here theta. We're not sure what it is right now. And then we can draw a couple conclusions. So if I set up some of my right triangle trig expressions from the last video, I have the sine of theta equals opposite over hypotenuse, so y over 1, and the cosine of theta equals adjacent over hypotenuse, so that's x over 1. Now I know that when I divide by 1, the value doesn't change, so what I just learned was that the value of y here, the height of that triangle, is the sine of theta, and the value of x, the base length of that triangle, is the cosine of theta. And so I now have a lot of information about my coordinate point, xy, and if I wanted to, I could write that coordinate point as the cosine of theta sine theta. One last thing that I can notice is that the tangent of theta is opposite over adjacent, so that's y over x. I also remember that the tangent ratio was first derived from a slope ratio. So the tangent of theta is also the slope of the line. And this is going to be really important when we're trying to interpret what it means to have the tangent of a certain angle measure, or the sine or cosine of a certain angle measure. So as I look at my unit circle, I've got 4 quadrants. Quadrant 1, 2, 3, and 4. The sine, cosine, and tangent of theta will be either positive, negative, 0, or undefined, depending on where we are on the unit circle, and knowing the names of the quadrants will just help us communicate more easily about what's going on. So if I am looking at the point 1, 0, and I draw my line back to the origin to create my right triangle, I've actually created a flat line. It's not a triangle, but we can think of it as a triangle that has a height of 0. So we know that this point is at x equals 1, y equals 0. So right here, the cosine of theta equals 1, and the sine of theta equals 0. That makes sense because the cosine of theta is the length of the base of the triangle, which, because it's all the way out to x equals 1, is 1 unit. And the sine of theta is the height of the triangle, which is 0 because it's been flattened to become a one-dimensional line. So if I look at a point that is squarely in the first quadrant, I can create this right triangle. And now I see that the height of my triangle is positive. So in the first quadrant here, the sine of theta is positive, and the base length is also positive because it's on the right side of the y-axis. So the cosine of theta is also greater than 0. Looking in quadrant 2, I've got a positive sine still, but my cosine is now negative because I'm on the left side of the x-axis. I'm to the left of x equals 0. So the cosine of theta is less than 0. In the third quadrant, I'm looking at a triangle like this, which has a negative cosine for the same reason, and a negative sine, because now the height of my triangle is below the x-axis, so it's at a negative y value. And then looking in the fourth quadrant, I can create a triangle here that has a negative sine, because it's below the x-axis, but my cosine is positive again, because it's on the right side of the y-axis. So if we look at the other points that are in between the quadrants, we would have a straight vertical line at 0, 1. That would give you a cosine of 0 and a sine of 1. Okay, and we can do the same type of thinking for the other 2 points at -1, 0 and 0, -1. Because we know the coordinates, the x and y values of the coordinates of those points, we know what sine and cosine are at those points without doing too much thinking. The last thing we want to think about is the tangent. So in quadrant 1, my slope is positive because my line is increasing as I scan from left to right. So in this quadrant, the tangent of theta is greater than 0. In the second quadrant, my tangent or slope is negative, so it's less than 0, because as I scan from left to right, my line is decreasing, its outputs. The tangent is positive, again, in quadrant 3, because my outputs are increasing as I scan from left to right, and negative in quadrant 4, because my outputs are decreasing as I scan from left to right. So now that we know a little bit about sine, cosine, and tangent on a unit circle, we need to look at the difference between radians and degrees so that we can create a fully labeled unit circle using radians, which are the more conventional way of measuring angles in applied mathematics fields, like engineering or optics. So for all of your mathematical careers, we've used degrees to measure angles, and we know that a full circle has 360 degrees. So if I'm labeling this angle measure as 0 degrees, I would have 90 degrees up here, 180 degrees is a semicircle, 270 degrees, and then 360 degrees, which is at the same point on the unit circle as 0 degrees. The fact that there are 360 degrees in a full circle is a really arbitrary measurement, and so a different way of describing a full circle is by saying that there are 2 pi radians. So we would have 0 radians at our starting point, and then pi radians is the same as 180 degrees. And so halfway between 0 and 180 degrees, I would have pi over 2 radians. And at 270 degrees, I would have 3 pi over 2 radians. 3 halves of pi radians. Okay, so 0 radians is the same as 2 pi radians. Remember that a radian, a single radian, is defined as the length along the circumference of a circle that is equal in measure to its radius. So I mapped out a radius here, and remember that in our unit circle the radius is 1. And so 1 radian would be a length along the edge of the circle that's about that long. And I just eyeballed that. So I tried to make the length of my curve the same length that I drew my radius in on the right side here. Because the circumference of a circle is 2 pi times the length of the radius, there are 2 pi groups of a length of r in a full circle, around the outside of a full circle. So if we keep in mind that 1 radian is the angle measure that marks out a length along the circumference of 1 radius. So if there are 2 pi groups of the radius length along the outside of a circle, then there must be 2 pi radians inside the center of the circle. The 2 pi radians, which is the angle measure of the full circle. So we can also see that for these dots that are marked out on my unit circle, there are 1, 2, 3, 4, 5, 6, 12 of them within 180 degrees. So there must be an angle measure here of 1/12 of pi radians. And so we can count up by twelfths of pi and simplify those fractions as we go. So here I would have 2/12 of pi radians, which is the same as pi over 6, 3/12 of pi radians, which is the same as pi over 4, and so on. We want to take a minute to look at some special right triangles so that we can figure out the exact values of sine and cosine for some of the angle measures in our unit circle. So starting with an equilateral triangle with side lengths of 2, if I cut that triangle down its center, I will have created 2 right triangles, and the side length, the hypotenuse, will still be 2. That wasn't changed. I'll have a 90-degree angle here. My 60-degree angle on the left side didn't get changed, and this 60-degree angle up top got cut in half, so that's now 30 degrees. So this is a 30, 60, 90 triangle, and my base length got cut in half, so it's now a length of 1. I can use the Pythagorean theorem to find out that the height is the square root of 3. So using our trig ratios, we can find the sine and cosine of 30 and 60 degrees using this triangle. So the sine of 60 degrees is opposite over hypotenuse, so that's the square root of 3 over 2. And the sine of 30 degrees, using the other acute angle, is opposite over hypotenuse. The opposite leg to 30 degrees is 1, and the hypotenuse is still 2. The cosine of 60 degrees is adjacent over hypotenuse, so that's 1 over 2. And the cosine of 30 degrees is adjacent over hypotenuse, so that's square root of 3 over 2. We can see that the sine and cosine flip-flop when we go from 60 degrees to 30 degrees, and that's because we've switched which acute angle we're looking at, and so the opposite and adjacent legs are switched in our ratios, but the hypotenuse stays the same. The other special right triangle we want to look at can be created by cutting a square along its diagonal. So when I do that, I still have a right angle in the bottom right corner, and both of my acute angles are 45 degrees. So this is a 45, 45, 90 triangle. My side lengths of the legs are still 1, and I can use the Pythagorean theorem to find out that the hypotenuse has a length of the square root of 2. So again, I can find the sine and cosine of 45 degrees. When we switch acute angles in this case, it stays the same because we're still using 45 degrees. So the sine of 45 degrees is opposite over hypotenuse, 1 over the square root of 2, and the cosine of 45 degrees is the same thing, 1 over the square root of 2. Now, mathematicians don't like to leave a square root, an irrational number, in the denominator, and so to rationalize our denominator, we're going to multiply by the giant 1 square root of 2 over square root of 2. Anything divided by itself has a value of 1. Multiplying by 1 doesn't change the value of your original number, and so we can do that without making the number bigger or smaller. So we find out here that the cosine or sine of 45, because again those are the same, is the square root of 2 over 2. And that's because when I multiply these fractions together, the square root of 2 times 1 is square root of 2. And the square root of 2 times itself is the same as writing the square root of 2 squared. And the square root of 2 squared is just 2. So I've got a picture of quadrant 1 of my unit circle that's totally filled out, and I just want to briefly explain how I got some of these values. We already talked about 15 degrees, because that's 1/12 of 180 degrees, which is also pi radians. 180 degrees is pi radians. Then 15 degrees is the same as 1/12 of pi radians. 2/12 of pi radians would be 30 degrees. 2/12 of pi reduces to pi over 6. 3/12 of pi reduces to pi over 4, and so on. And then I've got some of my coordinate points here by either using Desmos or a graphing calculator, or using my special right triangles. So looking at this one here, I've got an angle of 30 degrees, which is the same as pi over 6 radians, but I'll use degrees for right now. And I know that my hypotenuse is always 1. So if I turn this into my equilateral triangle, I can see that the height would be 1/2, because it's going to be half of the original equilateral side length. And then this leg here is the square root of 3 over 2, because it's the square root of 3 times bigger than the other side leg. Remember that our original 30, 60, 90 looked like this, with 60 degrees here, 2, 1, and the square root of 3. So the two legs are different by a scale factor of the square root of 3. So when I want to do the cosine of 30 degrees, I've got adjacent, which is the square root of 3, over hypotenuse. Anything divided by 1 is itself. So the cosine of 30 is the square root of 3 over 2, something we could have also derived using our original 30, 60, 90 triangle. So I've filled in as much as I can in that first quadrant. I've used degrees and radians, and I've labeled all of the xy coordinates. Remember that in the unit circle, the x coordinate is where we write the cosine of theta, and the y coordinate is the sine of theta. And just a reminder about why that is, if that's my coordinate grid, here's my unit circle. I'm going to connect to a point and draw my height down there. There's my theta. This is the point x, y. And so it is x units past 0 on the x-axis and y units above 0 on the y-axis. The hypotenuse is 1 because I'm in a unit circle. And so the cosine of theta is x over 1, which is just the same as x. So the x-coordinate is the cosine of theta. The y-coordinate is the sine of theta. And now I can use the fact that circles have symmetry to fill in quadrants 2, 3, and 4 on my unit circle. So I'm not going to write on the first quadrant of this bigger unit circle, but if I wanted to fill in this point, for example, I know that is 1, 2, 3, 4 groups of pi over 6 radians past 0. So 4 pi over 6, which is the same as 2 pi over 3 radians. I can also write that as 120 degrees. This point has the same height as pi over 3 radians, so I know its y-coordinate, and it is the same distance away from 0 on the x-axis, except that it's negative because it's to the left of the y-axis. So whereas for pi over 3, my coordinate point was 1/2 square root of 3 over 2, now I've got a coordinate point of negative 1/2 square root of 3 over 2. So remember that we figured out where the cosine, sine, and tangent were positive or negative, depending on whether you're in quadrants 1, 2, 3, or 4. And so we're going to have the same values for the cosine and sine along our unit circle if we're using these 15-degree points, but the sine or cosine could either be positive or negative depending on its quadrant. So you can go ahead and fill in the rest of your unit circle, and that will help us when we try to evaluate trig expressions. So I have a couple examples here. The sine of pi over 4 is in our first quadrant, so I'm just looking at this information here. Sine is the y-coordinate, and in this case x and y are the same, so I can evaluate this to be the square root of 2 over 2. The next one is looking at the cosine of 2 pi over 3. That's not in my first coordinate, but it's going to have the same base length and height as pi over 3. I just have to consider whether the value should be positive or negative. So cosine is the base length of my triangle, and I'll be at 2 pi over 3, which is in the second quadrant, and so my base length will still be 1/2, but it's 1/2 to the left of x equals 0, so it's going to be a negative 1/2. And we've got the sine of 7 pi over 6. 7 pi over 6 has a reference angle of pi over 6. It's 1/6 past a whole radian, so it's 1/6 past 180 degrees, which means I'm going to be in the third quadrant, which I can imagine like this. Sine is the height of the triangle, so this one has a height of 1/2, which means I'm going to be 1/2 below the x-axis. So the sine of 7 pi over 6 is negative 1/2. So looking at two more examples with tangent this time. The tangent of 3 pi over 4, I'll need to use pi over 4 as my reference angle. And I notice here that the x and y coordinates are the same at pi over 4 radians, or 45 degrees. So I'm going to have a 45, 45, 90 triangle, but 3/4 of pi is in the second quadrant. And so this has a slope of -1, because rise over run is going to be the square root of 2 over 2 over negative square root of 2 over 2, which is a value over itself. So this is going to evaluate to -1. I can verify that the sign should be negative by just looking at the slope of that line, which decreases as I scan from left to right. The tangent of pi over 6 is in the first quadrant, so pi over 6 is its own reference angle. And I know that tangent is the slope of this line, so I want rise over run, or the y value, divided by the x value. I've got division of fractions, which I can rewrite as a multiplication problem. Dividing by a number is the same as multiplying by its reciprocal. And so I can simplify this to be 2 divided by 2 times the square root of 3, which is the same as 1 times the square root of 3. Now remember that those mathematicians don't like to leave irrational numbers in the denominator, so I'm going to choose my giant 1 carefully here, and I can simplify this to be the square root of 3 over 3. The sign should be positive because I'm in the first quadrant, so my slope is positive. We'll be connecting all of the math that we just did involving trig expressions and the unit circle to graphing trig functions in the next 2 videos. So make sure you catch those, do the practice problems, and schedule a retake when you feel ready.